Method of
Resolving.
Method of resolving. So what does the word resolving mean? I think I told you that. Splitting a vector into two components. Now, if I have a displacement, now I'm talking about displacements right now because we have gone through displacements and velocities, not many, right? Now, in future, you will see so many more vectors, forces, momentums, and electric fields, magnetic fields. You'll be talking about many vectors. And then the same thing applies everywhere. Now I'm talking about 40 meters. Later on I might say, 40 newtons. But it is applicable for what? So this is the starting point, this is the ending point. And this is at an angle of, let's say 53 degrees. So one way of telling a person, go from here to there, is by telling him, all right, go 40 meters displacement at 53 degrees north of east. And then everything is clear. Right?
Yeah.
Is that clear,
Yeah.
Brendan? So 40 meters at 53 degrees, sit straight. Yeah, I'm not. All right, 40 meters at 53 degrees north of east, and then that person actually says, okay, that's east, that's north, 53 degrees, and then walks 40 meters, he's at that spot. Correct? Now, what is another way of doing it is give the components. Instead of telling him to go there straight away, tell him how much along the east and how much along the north. Those are called components. This is one component, and this is the other component. So tell him, go east this much and go north that much, and you're at the destination. So splitting them up into components is called resolving. Splitting into components is called resolving. Now, how many different ways can you actually reach there by two displacements? Infinite, right? So I can go here and then reach there. I can go there and I can come back here. I can go here and come back here. I can reach this spot by two displacements in infinite ways. But we're not interested in all those infinite ways. We are interested in the ways which are 90 degrees to each other. We need a right angle triangle. The two components have to be along the x-axis and y-axis, or along the east and north, or east and south, or west and south, one of them. So therefore it will be always at 90 degrees to each other. Now, method of resolving is kind of opposite of finding the resultant. How do you find the resultant? Yeah, so you were given this, and you were given this, and I told you what is the resultant. And what you did using Pythagorean theorem, you just did this. And this is pretty much the opposite. So if I give you this and this, you can find this, and the angle too, right? And this is the opposite. I give you this and the angle, you want to split it into the components. So we call this x component because it looks like along the x-axis, and this is the y component. In future, I will not use the word x component. Instead, I will call this adjacent component. You know why I'm calling that adjacent component? Because it is touching the angle. That's it. Because it is adjacent to the the angle is here and this is touching the side, and so I call it adjacent component. And this one I will call it opposite component. So when I look at this side, I'll say, all right, I want the opposite component. I want the adjacent component. So you also call it the same way. Instead of calling it x and y component or east and north component, use adjacent and opposite components. Now, what trigonometric ratio connects this side and that side and the angle?
Sine. Cosine.
Cosine. Trigonometric ratio. Cosine of the angle. So cosine of 53. Cosine of 53 is equal to x over 40. And therefore x is equal to 40 cosine 53. Well, it comes out.
X equals 24.1
24.1
meters.
Now, what connects the angle and this side, which is the opposite component, and the 40?
Sine.
Sine of 53 degrees is equal to y over 40. So y is equal to 40 sine 53. Whatever it is. How much is it?
31.9
31
meters.
So you see how we split into two components? So instead of telling a person, go 40 meters at such and such an angle, you can just say, go 24.1 meters. In fact, this is not drawn to scale. Can you see that?
Yeah.
The angle I've drawn is not looking like 53, should be somewhere here. And that's why it looks kind of awkward. This is 24 and that is 31. That's a drawing. So when you're drawing diagrams, you always try to attach a little bit of scale sense. Okay? When you're drawing something big, 60 degrees should look like 60 degrees. 53 degrees should look like that. Or 70 degrees should look like 70. 10 degrees should look like 10. Okay? That way you will be more realistic when you look at the diagrams. Alright, so instead of telling the person go at this many meters at 53 degrees, you can just say go 24.1 that way and then 31.9 that way, and you're at the spot. This is called resolving. So, splitting a single vector into components. Yeah.
So you said we need to make a right triangle. How would we do that on multiple vectors? You said we couldn't use the cosine or sine rule on multiple.
Yes. Just wait. You will learn it very soon. Today. All right. You'll get there. You'll get there. Now you understand the method of resolving?
Yeah.
That's it. So how do you find the resultant? How do you find a vector's components? Very simple. Look, if I have this one as 100 meters, and if this angle is 35 degrees, I want the x and y components. Immediately what you do is, you don't have to sit and do these things again in future. You do this. Thought process should go like this. What component is this, adjacent or opposite? So it will be 100 cosine 35. Cool. What component is this, opposite or opposite? So it's 100 sine 35. Now these things should be done quickly. So you're not going to write this and this all the time. We know adjacent is cosine, right? Mm-hmm. So this vector times the cosine of the angle gives you the component. But never attach x-axis component or x component to cosine and y component to sine. That is dangerous. That's what I'm saying. I won't call it x component, y component. I'll call it adjacent component and opposite component so that you don't make mistakes. I'll show you another example. This is your x-axis and y-axis, and here is a vector. (40°), 80 meters. In order to go from here to here, or instead of going from here to here, we can go there by two ways, right? Which are the two ways? Always try to go along the angle first, so that you have reference. So you go this way, and then you go this way. Right? What component will you call this?
Sine.
Adjacent component. Can you see this? Because this is the angle, and this side is touching that angle, so you call it adjacent component. And so what do you use?
Cosine.
And this side is the opposite side of this, and therefore you use now. That's the reason why I said don't attach x to cosine and y to sine. That's dangerous. Just say adjacent component. Is that what you're looking for? Then cosine. Opposite component. Is that what you're looking for? Sine. But there's one more thing to be taken care of. Is this component along the positive y-axis or negative y-axis?
Negative.
So you have to put a minus sign. You understand that? Is this component along the positive x-axis or negative x-axis?
Negative.
Let's put a minus sign. So far, did it make sense? Splitting is easy. Good. Let's work a problem using this idea, method of resolving, and you'll see how to do problems in future. All right, copy it.
Yeah.
Jackson? The procedure of how to do it. Let me give you vectors, multiple vectors. Here is one vector. Here is one vector. 30 meters east. There's another vector here. "65 meters at an angle of 50 degrees. What do you call this? 50 degrees what?
West of south.
West of south. You understand why it's the west of south?
Yeah.
Because that's your reference line, that is south. So you're going to the west from the south. Alright, so west of south is this one. Then you have another vector, which is this. South. And there's another vector. "80 meters, 40 degrees. What do you call that? 40 degrees? North of west. This is west.
Yeah.
And therefore, towards the north from the west. So north of west. You're going, starting from the west and going towards the north. So it makes sense. Make sure that this is clear. I don't want any confusions of you putting things the other way around. And then one last vector. "50 meters at an angle of 60 degrees. What do you call that? Everyone should think, everyone should agree with that answer, and make sure that you understood what it is. Yes, what is this? North of east. Alright. So here are 5 vectors, and we want to find what? The resultant. So imagine someone went 30 meters east, then he went 65 meters west of south at this degrees, and then he went 80 meters at 40 degrees north of west, and then he went this way, and then this way. Where is he ultimately? Now, methods of doing it: scale drawing, not very accurate. Next one, sine cosine rules. Sine cosine rules, troublesome. Why? Because if you want to do these two, finish that, get the new resultant, use that with this. Then get a new resultant, use that with this. Get a new resultant, use that with this. It's a long process. This period is not enough for it. Yeah.
Does it matter if you go? Does it have to be like in exact order? Or can
You mean the scale drawing or which method?
No, I mean like.
Doesn't matter.
Like just choose one.
Doesn't matter. Order doesn't matter. You can add them. That's what I told you in scale drawing. You can add it in different orders and still get there. Yes.
Are there any situations where you have to use like sine or cosine rule and you couldn't use method of result?
Never. Never. So if you don't know sine and cosine rules, you can just take it off completely from your head. It's just a mathematical tool. It's just a mathematical tool that you can use. That's there for the taking. Now, if method of resolving is not very clear to you, then go back and do that, cosine and sine rules. But this method of resolving should be easy to any person, because if the other two are going to be more complicated, because the first one is drawing and all that. Now, how do you go about doing this? You're going to do all at once. All at once. Just look at the order of things and then everything should be alright. Now, what you do first is make a table. Make a table. This is going to be vector. Which vector you're talking about? And this is going to be the x component. And that's the y component. Means anything on the x-axis comes here, anything on the y-axis comes here. Now, since I did not call it by some names, I have to give some names to these vectors. So let me call this A, let me call this B, let me call this C, D, E. Doesn't matter which one's called what. So I'm calling it A, B, C, D, E. So that is pretty much what I'm going to do here. I want vector A's components, vector B's components, vector C's components, vector D's components, and vector E's components. So let's start with vector A. Now remember one more thing. What is this component supposed to be? Look, if a plane is taking off like this, if a plane is taking off like that, okay, pay attention. If a plane is taking off like this, the plane is flying with a certain speed, right?
Yep.
This way? Yep. Now imagine a truck is driven on the ground at the same speed as the shadow of this plane is on the ground. That will be the x component. You understand this? Or okay, let's say it's noon and then sun is shining from above. The plane is flying like this. What about the shadow of the plane? Will it be going at the same speed as the plane? No, it will be going slow. On the ground it will be slow because the plane is going at an angle. What the shadow is doing is it's only covering the horizontal component, only this. Make sense? So if there is a truck that wants to be under the plane all the time, what speed should the truck be moving at? What speed? It should be moving at a speed which is the horizontal component of this vector. You understand this? So that's basically the idea of components. So let's start with A. How much of A is along the x-axis?
Meters.
How much?
30 meters.
30 meters. So I'm going to put 30 here. But before you do the next thing, is it positive 30 or negative 30? That should be the next thought that should come to you. Because you're dropping a component.
Positive.
Positive? Okay, put positive. So I will encourage you to put the positive and the negative signs. So that will force you to think about it. You understand? Don't blindly throw the numbers in and go on. After throwing the numbers, think, is it positive or negative? Let me check. Oh, it's positive. Good. What is the y component of this? How much of this is along the y-axis? None. It's purely going along the x-axis. So there's nothing along the y-axis. Good. We're done then. Now let's go to the second vector. For the second vector, first job, splitting into components. So here are my components. And it's always good to draw the components starting from the angle itself. You don't want to go here. Start from here. This is one component. And this is the other component. Is that good? Now how much is this component? 65. Always say the vector first.
65 cosine.
65 cosine 50. And is it positive or negative? It's negative, so minus. That is which component? X or Y? That's Y. So make sure what it is. But anyway, first do the splitting part of it. Don't confuse the entry at the same time. Just do this. What is this component? It's the opposite of 50. So 65 sine 50. So easy to split it. You don't have to use trigonometry. So 65 cosine 50 downwards. And what about this? Is it positive or negative?
Negative.
Now let's transfer it onto the table. What do you want first? X component? Which one is X component? This one?
No.
This is X component, right? And how much is it? Minus 65 cosine 50. How much is it?
Negative 49.8.
Negative 49.8. Put that here.
Negative
49 or 41?
41.
No, it's
49.
49.
65 sine 50.
49.8.
Negative 49.
Yeah.
Alright, so we have negative 49.8. What about the other component? How much is this?
Negative 41.
Negative 41.8. Is 8 also?
Yes.
So negative 41.8. Over. Now, of course, it's meters. I'm not writing the units there. Those are all temporary steps there, so just don't worry about it. I'm done with B. Let's go to C. I'm going to split the C now. So this one is, that is one of the components, and this is the other component. Now what is this?
50 cosines.
50 cosine 60. Immediately you pounce on the cosine because it is the adjacent component. Finished. And this is the opposite component of 50 sine 60. You know, follow these things and you'll find yourself coasting pretty well without any issues here. 50 sine 60. Numbers. So the horizontal component, both are positive. So this is going to be a positive 25, and that's going to be a positive 43.3. Now let's go to D. How much of this is along the x-axis? None. How much of this is along the y-axis? Negative 40, because it's downward. See, you're doing little things at a time. In this case, you're doing only little things at a time, but be careful about it. Okay? Just be careful with the plus, minus, and the components. Simple. Let's go to E now. I'm going to split E into components. This is one component, and that's my next component. Do you understand how to split it? Like the way I'm drawing it. I'm just going along the angle first, and then going perpendicular to it. So what is this component? 80 cosine 40 with a minus sign though. How much is this?
Negative 61.
And this one is 80 sine 40. How much is it?
51.4.
51.4. Now, let's go to the entry point. Yes.
So, how do you know that the x was negative? Shouldn't that have been on the positive side of the axis and just be facing the other way?
You mean this one?
Yeah.
Look at the arrow.
So the arrow.
Yeah, I mean, this is where you want to go. Starting point is here. That's your origin. That's your origin. And when you want to go this way, you're going to the negative x-axis. And when you go this way, that's a positive y-axis. So that's positive, and that's negative. So transfer it now. Any questions, let me know. All right, what is the x component of E? Minus. And what's the y component of E?
51.
Plus 51.4. That's the simplest job that you've done so far. Just splitting each one and then writing in the proper columns. After that, you want to find out the resultant. How do you get the resultant? A plus B plus C plus D plus E is supposed to give you R, right? And so when you add all this, you're supposed to get the resultant's x component. This will give you the resultant's x component. Only the x component. So add them all up on your calculator. 30 minus 49.8 plus 25 minus 61.3, and what is that?
Negative 56.1.
Negative 56.1. Now adding all these will give you the resultant's y component. Add them up. Negative 41.8 plus 43.3 minus 40 plus 51.4. Positive, negative. 12.9. Now you got the x and y component of the so-called answer. You're just so close now. You got the x component of the answer and the y component of the answer. Now what do you do at this point is to make a new sketch, new axis, and on the new axis you're going to draw these out. Let's go to the x first. Minus 56.1. So where do I draw this? To the left. And there it is. So minus 56.1. You don't have to put the minus sign once you know it is drawn correctly. See this? Don't put the negative sign, because you've drawn the arrow in the right direction. So if you put minus again, it may look like you're going to switch it again, right? So leave it there. So this is 56.1. And then followed by that, you're going to make a y displacement of 12.9 from here. So you're going, that's positive. So you're going up. 12.9. See, I'm drawing it to proportion so that your answer should be more realistic. Where is the resultant? If this is the x component of the resultant, this is y component of the resultant, where is the resultant?
It's the hypotenuse.
It is the ultimate tail to the ultimate head, which is the hypotenuse of this triangle. And that is the resultant. How do you find it out? Do it. So R, the magnitude of R is square root of 56.1 square plus 12.9 square. Remember, I'm not using any minus signs anyway. No need to use any minus signs. Just look at that triangle. And how much is this?
57.6.
57.6 meters is my final displacement. But your answer is not finished until you give the direction. So you need to find the direction. You need to find the direction. So to find the direction, tan of this angle is supposed to be the ratio of opposite to adjacent, so do that. Okay, I'm going to take off the space. Tan of the angle is 12.9 over 56.1. Again, reminding you, never put the minus signs here. You already drawn it to the right shape, right position. You don't. Okay, so what is theta equal to? Do that. Second function second function tan, and that. What do you get? Second function
Well,
tan, which is tan inverse,
12.9.
Is it 12.95?
12.95, which is basically 13 degrees. Now you have to say which way. 13 degrees where?
West.
What is that?
West.
North of west. Over. So instead of telling that person, go here and go here and go here and make all those displacements, you can just say one answer in the end, which is just go 57.6 meters, but make sure you're angled at 13 degrees north of west and you reach your destination. Get it? Is it clear? Now, what is the difference if I give you 10 vectors? Yeah, you just have a bigger list, but ultimately you're doing the same addition, and this process is exactly the same. This process is exactly going to be the same. The only thing is the list becomes a little longer. But yes, it is an easy method. But are there chances of mistakes? Plenty. Plenty of mistakes can creep in. You miss one of those negative signs by carelessness, the whole thing is over. You understand? So the method of resolving is a quick method of getting to the resultant, no matter how many vectors are involved. Now, if only 2 vectors are involved, you should be able to do it. You know the one which we did with cosine and sine rules? Just ignore that cosine and sine rule method and do it this way. Treat it as A and B, and then just do it by method of resolving and see if you're getting the answer. You understand that? And once you get that answer, you are kind of okay with the method of resolving. It won't take much time because there's only A and B there. One is, I don't know which way it is. One is like this and the other is like that, right? And you'll have only 2 vectors. You split them, and finally you get the answer much faster. Well, not now, you can do it at a later time. But you understand the method of resolving? Yes. If you don't understand it, go back to the video and just go through it step or whatever. Now, so far what you have done is kinematics in 2 dimensions, but everything horizontal. Like you're going east, you're going this, you're going that way. You know, it's all in one plane. But now we're going to talk about kinematics in 2 dimensions, but using the gravity also. Using gravity as well. Now, you've done problems in equations of motion, like if I take this and toss it up, how long will it take for it to come back? Right? What do? Use equations of motion. Just use equations of motion. How long it takes to come back. use the equation of motion. Now this time we're going to project it. Like it's not like this straight away. It's going to be the other way. Like toss a football. That. Now let me ask you one question here. For this scenario, look at this marker. I'm keeping the marker right at the edge of the table. The marker is kept at the edge of the table and it falls. Good?
Yeah.
Great. Now, watch the same marker this time. I pushed it horizontally and it landed over there. Question, which took more time to land, that or this? Answer? It's the same amount of time. It takes the same time for this marker to land here compared to the other one. The reason is that what is taking the marker down is purely it's a gravity that was doing the job of pulling it down and making it reach the floor. Now, why did this thing go that far? Is because I gave it an initial push horizontally. So when you give it a push horizontally, it is doing two movements now. The horizontal push that I given is going to continuously stay there. It's going to go on. But gravity is also going to come in. So therefore, it is moving horizontally at the same time it begins to fall. So the falling concept is still there. And therefore, the time taken for it to land is exactly the same. Okay? What is this?
Marker.
It's a gun. What is this?
Bullet.
Good. Got it. 50%. Always good. All right. So if I'm actually aiming this gun horizontally like that, and if I'm shooting this bullet, and by some default, some problem, the gun is not working properly, so the bullet just trickles down like that. The bullet, it's a faulty gun. The bullet just trickles and falls down. And then again I reload the gun, and this time I'm keeping it horizontal, and I'm shooting it, and this time it went all the way to Shelbyville Road and landed on the road. Which one takes more time to land? Neither. They both took the same time. If you're ignoring other consequences of physics, okay? So air resistance and so many other factors are there. I'm not including them right now. So a simple projectile like that is going to take the same time to land over there as well as this one landing down here if you're talking about a horizontal flow. You get it?
Yeah.
So what is happening to the bullet is the bullet is being pulled down by gravity. That's the same thing that's happening in both the scenarios. But in the second one, this was shot at a high speed, like 200 meters per second or 250 meters per second. And then it goes horizontally while it is doing the falling part of it. So two things are happening at the same time. One is a vertical motion, the other is a horizontal motion. And how do you tackle this so-called projectile motion? Is take them independently. The only thing that is common for a projectile motion is time. Time. The time taken for it to go vertically down is the time taken for it to go there. Another example. Watch me do this. When I'm taking this marker, I'm tossing the marker up and it comes back to my hand, right? So you see the marker going up and down. Now imagine I'm walking while I do the same thing. So if I'm walking and I do the same action, I'm walking and I do that. I tossed it up and it came back to my hands. But how did you see the marker going? Because I released it somewhere here and I caught it somewhere here.
Yeah.
But for me, it didn't appear that it was going forward. For you, you could easily see that it is going and doing this. That is a projectile motion in 2 dimensions. What you did earlier was a projectile motion in 1 dimension. We didn't call it projectile motion, but falling objects. Right?
Yeah.
So what I did was, so if you can be sitting inside a car and just tossing a tennis ball, will it come back to your hand?
Yeah.
Yes. An outsider standing on the road, how will he see the tennis ball going? It will be going like that. Why is the tennis ball going in a parabolic shape for that person? Is because he is an outsider. His frame of reference is different. So he sees the ball going up. Actually, the ball is simply going up and down, but the car is moving. So it's like this is a river. And imagine the river is absolutely still, and you swim across. Suppose you swim across and it takes 20 seconds for you to just cross the river. Okay?
Yep.
Now let's look at another situation, another day. You are attempting to swim through the river, but there is a river current taking you that way. There's a river current taking you that way. So your attempt is still the same. I want to just swim across. So what will happen is every time you try to swim across, the river is going to take you sideways. So there are two vectors now. One is this vector, and the other is this vector, right? You are going to go through the resultant. So the river is taking you here, and the river is taking you that way, and you're swimming this way. So ultimately, you're going to land here. How long will it take for you to land go from here to here? 20 seconds? Absolutely. Because every time you are doing your part, but the river is doing its part. You're doing your part, and the river is taking you sideways. So the sideway movement is actually something the river is doing. Get it? Whereas you are taking care of the movement across. The only thing is you are not reaching the same place. You are reaching a different place, a totally different distance away. Yeah, all that is fine, but you reach at the same time. So you can see how the projectile motion works on a similar principle. So let's dive straight into problem solving. Because you've done equations of motion. There's nothing that's greatly different here. The only difference is what's going on. So if I'm going to throw a projectile, let's talk about a simple projectile motion. There are two kinds of projectile motions you can think about. One is horizontal projection. What is that? Horizontal projection. Like I projected horizontally, like from this level, I projected horizontally like this way. Like the bullet, right?
Mhm.
For horizontal projection, that's one method. The other method is angular projection, like a football. Like you take a football and throw it. I'm going to throw it at someone who's dreaming. Okay. Horizontal projection is that way, and angular projection is that way. So we'll tackle both of them. Now let's talk about horizontal projection. Imagine there is a soccer ball or something here on top of a building. Let's say the building is 40 meters tall. We're solving a problem, and then we are getting to understand what to do. Okay?
Yep.
So the problem is, okay, the soccer ball is kicked at a speed of 30 meters per second. It's kicked at 30 meters per second horizontally, like flat on the ground. So that's the edge of the building. So it's shot like that. What will happen to the ball, as long as it is rolling on the top of the building, that's fine. But the moment it comes outside, there begins the free fall, correct?
Yeah.
That from there onwards, free fall. So what is the velocity with which it's going horizontally at this point?
30 meters.
What is the vertical velocity?
Negative 9.8.
Vertical velocity.
Zero.
Zero. It didn't start moving yet, downward. When you drop something, what's the initial vertical velocity?
Zero.
So there is no vertical velocity, but it's moving horizontally. But acceleration due to gravity is already coming into play. So what will happen as a consequence? After some time, the ball is here. How fast is it going horizontally? 30 meters per second. Vertically, it must have picked up some. You get it?
Yeah.
After some time, so you can see the resultant is somewhere here. So after some time, it is here. It's still moving at 30 meters per second horizontally. Vertically, it's moving faster. After some time, it is here. So you can see the trajectory of the ball. After some time, it is here. Still moving 30 meters per second. Vertically, it is moving faster. You can see the arrow length is bigger and bigger. Yes?
Would
Wind resistance we are ignoring for the time being.
I don't know, but I'm just curious. Would it function as like a function of acceleration for the?
It will decrease
horizontal
the
movement?
acceleration, yes. It will eventually make the acceleration zero.
Okay.
That's what we call as terminal speed. What is this? Okay. Jack. You didn't have this calculator all this time? You had one?
No, I have a brother.
Okay. Next, it's coming in landing. What is the horizontal velocity with which it's landing? And what's the vertical velocity? Something big. Right? Can you see the difference in the arrow lengths I've drawn? I didn't draw an arrow at all here because vertical velocity is
0.
Question is, where will it land? So I want to know this. Where will it land? So how do you tackle any projectile motion question? I'm going to show you the method. And just again, just like before, stick to that method. Okay, and what's the first thing that you should do?
Draw a diagram.
Draw a diagram. You don't have to draw all these arrows, no need. But draw a diagram, at least giving a visualization of what's going on. Okay? And then once you've drawn the diagram, the next thing that you should do is split the entire problem into two problems. Horizontal, vertical. You're going to split the entire problem into two problems. So don't make a tiny table. Make it a big one. You need more space here and here. You understand? Make it a two-table work. Be it any problem. All right. We are going to start here, end here. The journey starts here and ends here. For this journey, starting from here and ending here, you're going to put all the data that you know, horizontal ones on this side, vertical ones on this side. Don't mix it up. What do you know about the horizontal initial velocity? 30. All right. You got it. By the way, in the horizontal motion, there's only one equation that you're going to apply. Only one, not four. Why? Because there's no acceleration. Horizontally, there is no acceleration. So which is the equation without acceleration? X is equal to Vt. That's the only equation you're going to use on this side for all problems. All. X is equal to Vt is the only equation you're going to use on this side. On this side, of course, all the four. All the four can be used on this side. Okay? Depending upon the variables given to you. So we know the initial velocity is 30, and of course it's going to go 30 all the time. That's why I said acceleration is 0. You don't have to write acceleration 0 in future at all. Because it's going to be acceleration 0 for all problems. All. Any projectile motion problem, this is going to be 0. Yeah.
Well, why is it 0 when the acceleration of gravity is still...
But this is horizontal. I'm splitting it completely into two problems. The horizontal one, and the vertical one. Separate, completely separate. The only common thing is time. Only common thing is time. Alright, so we don't know anything else here. Nothing else. So let's fill up this one now. What is the initial vertical velocity? 0. Initial vertical velocity is how much is moving at that moment vertically? Nothing. What do you know about the acceleration? What else do you know vertically? Between this location and this location, vertical only.
40 meters.
Displacement? Yep. What is the displacement?
40 meters.
Be careful. How much?
Negative 40.
Negative 40. I told you, starting point here, finishing point this level. That means you're starting at this height and finishing down below. If you don't put the minus sign there, you're done. Completely, the whole thing is messed up. And so you got three things. What are you looking for? At least I need the time. In most problems, you need to figure out the time. In most problems, the time is the first thing that you need to figure out. Most of them. Sometimes you don't have to, but yeah, in this case, we need the time. So what you do is, okay, what is not important to us in this thing? What is not given to you? So which equation is not connecting final velocity? And don't write this anywhere here. Write it on the vertical side itself. Any equation you're going to play with, write it here. X is equal to? Now, I'm calling it X, but remember, this is the vertical displacement. So that's why some books kind of use delta Y for that. And they'll call it delta X here. But if you are not confused with horizontal displacement, vertical displacement, you're not confused with that, then it's fine. You know, those books don't draw tables like what I'm doing. They just write it down. So when you write it down, you can't write x and again x for this side and that side. You understand what I'm saying? So then you have to write delta y. You have to write everything. You have to write ax equal to 0. You have to write ay equal to, you have to put labels for everything because you're not doing it this way. All right, so what do you know here? Minus 40 is equal to, vi is 0, so this whole term is gone. This whole term is gone, 0. Minus 4.905 t squared. So negative 40 is equal to negative 4.905 t squared. What is t? 3 point. You'll get t squared first and then take square root of it. You'll get t squared first and then you take square root of that.
8.15494.
No, take square root of that. 8 point. What? Oh yeah. No. Yeah. Oh, then it's 2 point.
Yeah, 2.9.
2 point what?
2.9.
or 2.
Yeah, this is not our final answer, therefore keep the decimals and all that intact. How much is it?
2.855.
It's like,
Oh, it's 2.855?
8556.
Okay, 2.86 is good enough.
Yeah.
Seconds. So you got 2.86 seconds. What do you do now? Take this time and drop it on this side. Because I said the only thing that's common between the two sides is time. So 2.86 seconds. So far everything's okay? Yeah.
Can you explain what you did to get the time?
Yeah.
You divide 40 with 4.905. And that is the answer for t squared. Then take square root of that. These minus signs cancel off anyway. Now, if you forgot to put the minus sign here, you'll get t squared as a negative number and then you can't find an answer. Then it will remind you, oh, I missed the minus sign. So sometimes you may be lucky that the situation will tell you, oh, I made a mistake, let me correct it. But not always. Okay, so you got t squared is 8 point something, and then you get t as square root of that. Do you get it now?
Yes.
Once you get this answer, transfer it to this side. Transfer it straight away because you know that's supposed to be the same. Whatever is happening horizontally and vertically at the same time.
Yes.
Do it. And the only equation connecting here is x is equal to vt. Substitute. V is 30, time is 2.86, and what is your answer?
85.8.
85.8 or 86 meters. 86 meters is this one. That means the ball is going to land 86 meters away. This is excluding air resistance and all those factors. You get it? Now, how are other problems going to be? Now, this is a horizontal projection. Simple. I'm going to show you a sample, just a beginning of angular projection, so you will know what to do from there on. Is it clear?
Yeah.
For angular projection, this is angular projection. You shoot like that and comes here. So you release a football here. Suppose I throw something at 40 meters per second and at an angle of 60 degrees. The question is, where will it land? Or how high does it go? What will be the question? What you do first in this one is resolve the velocity into two components. Because when I say I'm throwing at 40 meters per second that way, I'm throwing with two velocities. What is the horizontal component? How much is the horizontal component of this? Quick. 40.
40. Sine 60. No, cosine 60.
Which is 20. And you want the vertical component which is going this way, which is this. What is what? 40 sine 60, which is 34.64. Right? So we have the two components. Now you can fill it up. What is the initial horizontal velocity? 20. What is the initial vertical velocity? 34.64. You see how we started?
Yeah.
That's the only difference in the problem. You split this into two components, and after that, you're good. You have everything there. What are you trying to find out? Where will it land? Right? Look, you know this. You know acceleration. What is the displacement vertically? What's the vertical displacement there? Yes?
Big zero.
A big zero. Vertically, it was here, now it's here. Very good. Displacement is zero. And then you have three things. You need to find the time. Use the same equation. Transfer the time here. So you got a number here. Then use x is equal to vt, and boom, answer. Get it?
Yeah.
Now, what if it does not land here, but it lands here? Still the same thing. But displacement won't be zero, but this time displacement is? And you can solve all kind of problems from projectile motion if you follow these things.